Hi! In this video we'll be looking at parametric equations, which you can use to describe all sorts of geometric objects. So for example, we'll see how to describe some line and how to describe a circle. And these parametric equations, they use vectors to describe these types of objects. So let's first look at this very simplest object that we think of, so a two-dimensional line. So we want to describe a line, so let's say in R2. Then to describe a line, we need two parts. So to write a geometric equation, a parametric equation, we write this vector xy, which is equal to, well, we need some point on the line. So some starting vector plus, well, the line has some direction. So we get some directional vector u. And in this direction, we need all of the points that lie on the line. So this is multiplied by some constant. Well, we take lambda in our case. So this describes the points on a line, and this t here is what we call the translation. Yes, the translation vector. And this u is called the basis of the line, where you can think of it as the direction of the line. So let's try to model this line here, this line L1 that we have in the picture. So then we write L1. So we have this xy. We need some point on the line for this first vector, so let's take this point 2, 3. So we have the vector 2, 3 plus lambda times, well, I already wrote the direction here because it's maybe a bit difficult to see from the picture, so we go 2 steps to the right, 1 step up. That's our directional vector. So this is the final parametric equation for our line. So this can be generalized not only to lines, but let's say we want to describe a plane in a 3-dimensional space. So let's look at a plane in R3. So now our we have 3 dimensions, so we get x, y, and z. And then we again have some translation vector, which is a vector to some point on the plane. And then we get the same as before. So now we have a line, but we do not only need a line, we need the entire plane. So we have 2 directions. So we also get some variable times another vector, let's say v. And these 2 should be vectors that are inside the plane, and they should not have the exact same direction or opposite direction, because then we would get a line again. So these need to not be parallel. All right, and now this is again the translation vector, and we say that u and v form a basis of the plane. All right, so that's how we can write a plane. Now let's take one final example. So we have this circle that we have here. So a circle cannot really be described by lines, or you would need infinitely many lines or something. So we have a bit of a different type of equation. So let's say we want a circle in R2 again. So simply in the plane. Then we again get only xy is equal to, well, we do get some starting vector, but now this starting vector does not point to a point on the circle, but we need this middle point of the circle. So let's denote it by m. So the vector to the middle point, plus, well, the radius of the circle, let's denote that by r, times cosinus theta sine of theta. And here, so our variable that was lambda and mu before is now theta. So if we increase theta, then we go around the circle, and exactly the values of theta that we get the entire circle is that theta should lie between 0 and 2 pi. Then we draw out the entire circle. So let's call this circle C1. So what is our description of C1 then? So C1, we can get xy is equal to, well, the middle point, which was 5, 2, plus, so the radius is 3 times cosinus theta sinus theta. All right, so we have seen some objects now. Let's try to do something with them. We'll try to find the intersection between two lines in this parametric form. So I already came up with a nice other line, so we will use L2, which is, let me see, xy, of course, is equal to, so we go through the point 1, 0, plus mu times minus 4 and 3. And we are going to compute the intersection between this line L1 and 2. So we're going to intersect L1, L1 and L2. And we should be really careful if we are going to try some intersection that we use some other variable in the two different equations. Because if we use lambda in both of them, these lambdas are not the same. So then we would get probably even no intersection point. So make sure that you always use two different variables. And then we will try to look at where the x's are equal and where the y's are equal, and that will give us some intersection points. So if we look at the x of this L1 here, that is equal to 2 plus, well, 2 times lambda, so 2 plus 2 lambda, and it should be equal to the x value that we have here, so that is 1 plus, well, minus 4 times mu. So let's get rid of these brackets here. Oh, it only got worse. Sorry. So minus 4 mu. And we can get a similar equation for the y. So we have 3 plus 1 times lambda, so simply 3 plus lambda, is equal to, well, here we have 0 plus 3 mu. So now we have a system of equations that we can solve. We can use this, solve this using Gaussian elimination that we'll see later on, but for now we'll just try to puzzle a bit with these equations and try to find a solution. So this second one looks rather easy, so let's first try to find some expression for lambda in terms of mu. So the second equation is the same as lambda is equal to 3 mu minus 3. And now we can plug this in to the first equation to find our solution. So if we plug this in to this one, then we find the following. So we get 2 plus 2, well, lambda we replaced by this expression, so 3 mu minus 3 is equal to 1 minus 4 mu. So let's try to get all of the mu things on the left-hand side and all of the other things on the right-hand side. So here we have 6 mu, and then we take the 4 to the other side, so we get 10 mu is equal to, well, we have 2 here and minus 6, so that becomes minus 4 on this side, and we already had a 1 here, so that is equal to 5. So that means that mu is equal to 1/2. All right, now we could compute lambda, but actually we don't really need it. We can already compute our intersection point only using mu, because this equation only contains mu. So our intersection point, so let's write our intersection point as x comma y. So the x, what will it be? Well, it is 1 plus, well, mu, which is 1/2 times minus 4, so minus 2. And the y value is 0 plus 3 times mu, so this was 1/2, so 3/2. So our final intersection point is minus 1, 3 divided by 2. All right, so that's how we can compute intersections using parametric equations. So in this video we have seen some different formulation of different objects. There are many more, and you can discover yourself how to describe more complicated objects. See you in the next video.